So what we are going to do is actually try to find out the slope at C location. So what we are going to do using the superposition method today is trying to divide your structure into two structures that is only under one load. So the first one we can find is going to be a cantilever with 4 kips. And the total length of the beam is going to be 11 feet. And then we also had another structure that we are going to have 6 kips here and only acting at 6 feet from the fixed end. So now the first thing we are going to do is try to find out which equation we can use from the table. Alright? So now the first question for the first structure. So let's try to name the structure first. For the first structure, it is a load acting at the end of the cantilever, so which means we are going to use the whole row here. However, can we use this equation to calculate the rotation angle at the C location? The answer is no, because in this equation, the theta max means what is the rotation angle at the end of the beam. However, in this problem here, we actually need to find out what is the rotation angle at C, which is 6 feet from the fixed end. So which means it will be better we are going to have the slope function. However, if we take a look at the whole row here, the first row, we cannot find any equation. It's named as a slope function. So what should we do right now? We need to find out the relationship between the slope and the deflection is actually takes the first derivative of the slope function, the deflection function, then we will be able to get the slope function. And this is why what we need to do for this problem here, we need to take the first derivative of this equation. So you're probably going to wonder why I didn't include the negative sign in this equation when I take the first derivative. This is because, let me draw the deflection curve. So under the 4 kips, the beam is going to deform like this. And under the 6 kips here, it will deform curvely for the first 6 feet. And then after that, it will be a straight line because we don't have load. So you can see for these two structures here, all the deflection is actually going down and the rotation is all counterclockwise rotate. So that's why I don't like to put any sign here because they were in the same direction. We just need to add them together. Sometimes adding sign will make you confused, so that's why I'm not going to do that. So now let's see. So this is the slope function. So what we are going to do is plug into the x so that we will be able to find out what is the rotation angle at C for the first structure. So the P is 4. The whole length for the beam is 11. And the X here is actually going to be 6. So if we do the calculation, we finally find out the rotation angle will be 192 over EI for now. So you're probably going to say, do I need to plug into the EI right now? The answer is no. Let's wait until you have to plug into, okay? Okay, so now let's take a look at the second structure. So the first question for you is, can we use this row here, the second row showing here, to calculate the rotation angle at C? The answer is no. Why? Take a look at here. For in order to use the second row, your load have to be acting in the middle of the beam. Is your load acting in the middle of the beam? The answer is no, because this side is 5 feet, another side was 6 feet. So it's not in the middle. So which means we cannot use anything in this equation. So now what should we do? So we need to focus on the slope. You can see from 0 to 6, it's a green line, a curve design, a curve deformation. And then after this, it's going to be a straight line. So you can see the rotation angle here and here is pretty much the same angle because the straight line. So what does this mean? It means that in order to find out the slope at C for the second structure is actually we need to find out if we had 6K acting at the 6 feet cantilever. What is the rotation angle at the end? So which means the theta 2, theta C at 2 structure, second structure is going to be using the equation maximum rotation for the load acting at the end. So which means we are going to use PL squared over 2VI. So which means, so remember, for this beam right now, the L is going to be 6 feet. So which means if we do the calculation, it will be 108 over EI. Okay, so now the total rotation angle at C will be these two add together. They were in the same direction, so we just numerically add them together. So for this problem, it's actually provided the cross-sectional area and the steel type, which means we will be able to find out the E is 29,000 KSI. And the modulus moment of inertia for W10 by 15 is going to be 69.4 inch force. So which means our rotation angle at C will be 300 over these two values. However, can you get the correct answer? The answer is no. Why? We need to watch the units. First of all, the load is kip. So which means we don't need to do anything for the kips here. And then KSI multiply inch, we eventually going to have inch square. So now let's check. So in this equation here, what is the unit for L? Is it in inches or feet? So you can see when we do the calculation, we always use feet as our unit. However, underneath for the denominator here, it is inch square. So which means we need to convert the feet to the inches. So we need to multiply 12. Then how many 12 we need to multiply? So now let's take a look at this equation here. You can see that's L squared. So which means we only need to multiply 12 twice. So which means if you plug into the equation in your calculator, you're finally going to have, and this rotation is going to be originally from here and rotate to here. So that's going to be your final answer to calculate the slope at C. So how could we find out what is the deflection at C? It will be much easier to do the calculation than the slope. Why? Because we can directly try to find out the deflection for the first structure. We can use this equation, and then we can try to add the deflection for another cantilever under the load at the tip here. So which means the deflection at C is going to be, it's all going down here. So we are going to have 4 times 6 square plus 6 kips times 6 feet cube. And then again, watch the units. You will be able to get the deflection is equals to 0.934 inch. And remember, from the deflection curve, we can tell that the deflection is going down.